Hi, welcome to Electrical Info YouTube channel. Subscribe our channel and share. Today we learn about HT11 kV control panel components. The HT11 kV control panel is an important component of high-voltage electrical systems. It is designed to control and regulate the flow of electrical power in the system, ensuring that it is distributed safely and efficiently. The control panel is made up of various components that work together to achieve this goal. Here are some of the key components of the HT11 kV control panel. Circuit breakers. Circuit breakers are essential components of any high-voltage electrical system. They protect the system from overload and short circuits by interrupting the flow of electricity when necessary. Isolators. Isolators are used to isolate specific parts of the electrical system for maintenance or repair purposes. They are designed to break the electrical circuit, ensuring that no current flows through the isolated part of the system. Protection relays. Protection relays are devices that detect faults in the electrical system and isolate the affected part of the system to prevent damage to equipment or injury to personnel. They are essential for ensuring the safety and reliability of the system. Meters. Meters are used to measure various parameters of the electrical system, such as voltage, current, and power. They are essential for monitoring the performance of the system and detecting any issues that may arise. Control switches. Control switches are used to turn various components of the electrical system on and off. They are typically mounted on the control panel and allow operators to control the flow of power through the system. Bus bars. Bus bars are used to distribute electrical power to various parts of the system. They are made of copper or aluminum and are capable of carrying high currents. Transformers. Transformers are used to step up or step down the voltage of the electrical system as needed. They are essential for ensuring that the system operates at the correct voltage level. In summary, the HT11 kV control panel is a complex system made up of various components that work together to ensure the safe and efficient distribution of electrical power. The circuit breakers, isolators, protection relays, meters, control switches, bus bars, and transformers are all essential components of the system, and their proper operation is critical for the reliable and safe operation of the electrical system. Next we learn about Enunciator. An electrical substation enunciator is a device that provides real-time information about the status of the substation equipment and system to the operators or maintenance personnel. It is a critical component of the substation control system and is used to monitor and manage the substation's various functions. An enunciator typically consists of a panel with a series of lights, gauges, and displays that indicate the status of different substation equipment, such as transformers, breakers, and switches. The enunciator's design is specific to the substation it serves and is customized to display the relevant information required to monitor and control the substation. The enunciator is connected to the substation's control system and is programmed to alert the operator when an abnormal condition is detected. The enunciator can provide visual and audible alarms to warn the operator of potential problems, allowing them to quickly take corrective action to prevent equipment damage or power outages. Some advanced enunciators also feature data logging capabilities, allowing operators to review historical data to identify patterns and potential issues. This feature can help to improve substation reliability and reduce maintenance costs. In summary, the electrical substation enunciator is a crucial tool for monitoring and controlling the substation equipment and system, enabling operators to respond quickly to abnormal conditions and maintain a reliable and efficient power supply. Next we learn about auxiliary relay. An auxiliary relay is a type of protective relay used in substations to monitor and control various substation equipment. It is designed to operate in parallel with the main protective relay and provides an additional layer of protection against faults and abnormal conditions. Some examples of auxiliary relays used in power transformers are Buchholz relay. This is a gas-actuated relay that is installed in the transformer's oil-filled tank. The relay detects the presence of gas in the oil, which is an indication of an internal fault, such as a short circuit or a winding insulation failure. When gas is detected, the Buchholz relay triggers an alarm and/or trip signal to the substation's control system. Winding temperature alarm. This type of auxiliary relay is used to monitor the temperature of the transformer's winding. It measures the temperature of the winding through temperature sensors installed on the winding or through the use of current transformers. If the temperature of the winding exceeds a preset limit, the relay triggers an alarm and/or trip signal to the substation's control system. Oil temperature alarm. This type of auxiliary relay is used to monitor the temperature of the transformer's oil. It measures the temperature of the oil through temperature sensors installed in the oil tank. If the temperature of the oil exceeds a preset limit, the relay triggers an alarm and/or trip signal to the substation's control system. Overall, auxiliary relays are an essential part of the protective and monitoring systems in substations. They provide an additional layer of protection against faults and abnormal conditions, helping to ensure the safe and reliable operation of the substation equipment. Next we learn about overcurrent relay and earth fault relay protection. An electrical overcurrent relay is a protective relay that is designed to detect overcurrents in an electrical system and provide protection against short circuits and overloads. Overcurrents can occur due to various reasons, such as equipment failure, external faults, or incorrect system operation. The electrical overcurrent relay monitors the current flowing through the system and operates when the current exceeds a preset level, indicating an abnormal condition. The earth fault protection relay is a type of protective relay that detects and provides protection against ground faults in an electrical system. Ground faults occur when an electrical conductor makes an unintended connection to earth, creating a path for electrical current to flow. This can result in damage to the system, equipment failure, and electrical shocks to personnel. The earth fault protection relay measures the current flowing from the system to earth and operates when the current exceeds a preset level, indicating an earth fault. Both electrical overcurrent relay and earth fault protection relay are essential for the safe and reliable operation of electrical power systems. These relays are designed to operate quickly and accurately to protect the system from damage and prevent hazards to personnel. In most cases, these relays are integrated with other protective devices, such as circuit breakers, to provide a complete protection scheme for the electrical system. Next we learn about TNC trip neutral close switch. TNC switch stands for trip neutral close switch. As its name, it is a 3-position switch. TNC switch uses to control the circuit breaker of the electrical system. The trip position is used to trip the circuit breaker, the close position used for closing the circuit breaker, and the neutral position is the default position of the switch. No output contact is connected from the neutral position of the switch. Why TNC switch use? We know the circuit breaker has the separate trip and close coil for tripping and closing of the breaker. To energize the trip and close coil, a DC pulse is required for less than 1 second. After the energization of the coil, the DC supply must be disconnected from the coil immediately. For example, if the DC supply is not disconnected from the trip coil, after closing the breaker, it will automatically trip. Similarly, for the closing circuit, the circuit breaker will close automatically after tripping the breaker. To avoid the problem, DC pulse to be applied to the coil for a smaller time. It may around 1 second or less than 1 second. TNC switch has the facility to provide a similar facility for giving the short DC pulse to the coil. Working principle. TNC switch has 3 positions: trip, neutral and close. The neutral position is the default position of the switch. At the position, no DC pulse or command will go to the trip or close coil. When it moves to the trip position, the NO, normally open, contact which is used for the trip circuit will get NC and it will give the DC pulse to the trip coil. When it moves to the close position, the NO, normally open, contact which is used for the close circuit will get NC and it will give the DC pulse to the close coil. The spring is connected to the operating handle of the TNC switch to stay the switch at the neutral position. In both the cases for tripping and closing, the operating handle of the TNC switch automatically gets back to the neutral position and NC contact becomes NO and it breaks the DC supply for the coil. Next we learn about digital voltmeter and digital ammeter. A digital voltmeter is an electronic instrument used to measure the voltage between 2 points in an electrical circuit. It operates on the principle of analog to digital conversion, where the analog voltage input is converted into a digital value for display on a screen. DVMs have a number of advantages over traditional analog voltmeters, including higher accuracy, greater precision, and the ability to measure a wider range of voltages. A digital ammeter, on the other hand, is an electronic instrument used to measure the electrical current flowing through a circuit. Like a DVM, a digital ammeter operates on the principle of analog to digital conversion, but it is designed specifically for measuring current. Digital ammeters are often used in conjunction with other test equipment to diagnose faults in electrical circuits, and they are available in a variety of sizes and styles to suit different applications. Both digital voltmeters and digital ammeters have a number of advantages over their analog counterparts. They offer greater accuracy and precision, can measure a wider range of values, and are generally easier to use. Additionally, many digital meters can be connected to a computer or other device for data logging and analysis, making them a valuable tool for engineers, technicians, and hobbyists alike. Next we learn about digital energy meter. A digital energy meter is an electronic device that is used to measure the amount of electrical energy consumed by a household or commercial establishment. It is a modern version of the traditional analog electricity meter. Digital energy meters provide accurate and reliable measurements of the amount of electricity used by a particular household or commercial establishment. They are equipped with a digital display that shows the amount of energy consumed in kilowatt-hours, kWh, which is the standard unit of measurement for electricity consumption. Some digital energy meters also have additional features, such as the ability to display real-time energy consumption data, which can help users better understand and manage their energy usage. They may also have the ability to connect to a smart grid, allowing for more efficient management of energy distribution. Digital energy meters are typically installed by utility companies and are used to determine the amount of electricity that needs to be billed to the customer. They are often more accurate than traditional analog meters, which can sometimes result in overcharging or undercharging of customers. Overall, digital energy meters provide a more efficient and accurate way of measuring energy consumption and are an important component of modern energy infrastructure. Next we learn about local and remote selector switch. An electrical local and remote selection switch is a device that is used to switch between local and remote control modes of an electrical system. It is typically used in industrial and commercial settings where a system needs to be controlled both locally and from a remote location. In local mode, the control of the system is performed directly at the site where the system is located. For example, if the system is a motor, the operator may use a local control panel to start, stop, and adjust the speed of the motor. In remote mode, the control of the system is performed from a remote location, such as a control room. The local and remote selection switch allows the user to easily switch between these two modes of operation. When the switch is in the local position, the operator can control the system directly at the site. When the switch is in the remote position, the operator can control the system from a remote location. The local and remote selection switch is typically a two-position switch, with one position for local control and another position for remote control. Some switches may also have an off position, which completely shuts down the system. Overall, the local and remote selection switch is an important component of industrial and commercial electrical systems, allowing for flexible control of systems both locally and remotely.